Hi, today I'm going to try and modify my arbitrary waveform generator to keep its output floating even when using remote control. You see, in normal operation, the AWG's ground isn't earth referenced, which is desirable for a myriad of reasons. When it's controlled by a computer using that USB port on the back, however, it shares the computer's ground, which usually is connected to mains earth. Obviously, if all I cared about was keeping the generator's outputs floating, I could just plug it into a laptop that's running off battery. But if anything happened to the generator, I could fry my laptop's USB controller, or even worse, the whole motherboard. So that's no good. Let's take a look at what's going on inside. There are three boards, namely the power supply, the front panel, and the main one, which generates waveforms completely in the digital domain using that big FPGA, and does all the analog stuff as well. Funnily enough, the giant FPGA is controlled by this little front panel microcontroller, which also handles remote control. Speaking of which, it turns out this generator isn't communicating using pure USB, but rather it has an internal USB to serial bridge. This makes things much easier, as providing galvanic isolation for USB is much more difficult than for simple UART. My first plan was to desolder all of these components and remake this part of the circuit on another board with added isolation, but I quickly decided against that idea when I saw this TTL out header. Apparently, it's connected straight to the USB to UART converter's output. This meant I could use an external converter and add galvanic isolation there, provided I cut these two traces on the PCB. That was a good plan. I had even bought two high-speed optocouplers for this purpose. But then I had an epiphany. I checked my box of microcontrollers and sure enough, I found a couple of ESP series microcontroller modules. Two ESP8266s and two ESP32s to be precise. Since I only need Wi-Fi and not Bluetooth or any of the more advanced features, I decided to use one of the former. I thought this simpler one would suffice. Anyway, what I wanted to do was use this ESP8266 as a Wi-Fi to UART bridge and plug it straight into the front panel UART cable, thereby not only eliminating the need for optocouplers, but for a 3-meter USB cable as well, as that's how far the generator is from my PC. An added benefit of this approach was that it would result in a much cleaner mod. No need for cutting traces, and the whole module could be neatly tucked away inside the case. With the battle plan ready, the first thing I had to take care of was adapting the ESP8266 for 5V operation. You see, this little devil of a microcontroller is a purely 3.3V device, meaning it cannot handle 5V, neither on its power nor signal lines. Luckily, an LDO could be soldered to the back of this white breakout board. An LDO, or low dropout regulator, is just that, a linear regulator with low dropout voltage, meaning it can convert as little as 5V into the needed 3.3V, instead of 7 or even more volts that would be required had I used a standard linear regulator, like the venerable LM317. I had a couple of AZ1117s from a previous project, so I soldered one of them in. I also had to desolder the 0-ohm resistor, which served as a jumper. That took care of the power supply side of this conversion, meaning it was time for the signal side. The transmit or TXD pin could be left alone, as it's an output-only pin, and 3.3V is high enough to be properly detected by 5V logic. The receive or RXD pin, however, needed to have a resistor divider soldered to it. If I recall correctly, I used one 10 kΩ and one 15 kΩ resistor, meaning that the resulting voltage divider converted 5V into about 3V. Close enough. Unfortunately, I had to solder a couple more resistors in before I could flash this microcontroller. Both reset and CHPD, aka enable, needed to be tied to 3.3V with pull-up resistors. After doing that, I pulled GPIO 15 down to ground with an 0805 SMD 10kΩ resistor, as this pin needs to be pulled down for both normal operation and flushing. And for that same reason, I pulled GPIO2 up to 3.3 volts. Last but not least is GPIO0, which needs to be either low or high during boot, depending on whether you want to flash the chip or not. What I did was to pull it up to 3.3 volts with yet another 10kΩ resistor, so that I could tie it to ground with a jump wire when I wanted to flash the chip, and leave it alone otherwise. Since I didn't want to solder in any push buttons, what I did to restart the MCU was to momentarily short the reset pin to ground with another jump wire. After all this, I could finally flash the module with the required firmware using a USB to UART adapter. Incidentally, this adapter was also a 5V one, so all the modifications done to this module were used here as well. Now to just plug it in and... that's weird. Flashing didn't work, it gave me a weird error. The internet said it was something to do with unstable power. No matter, I'll just solder in a decoupling capacitor and... yeah, I managed to flash it using a lower baud rate, but after that it went completely dead. And after all that soldering, god damn it! When not even more decoupling capacitors helped, I decided it was hammer time. And you know what else? I think it should burn. Burn in hell! Yeah, that's what I'm talking about. Well, that was cathartic. Anyway, it seems I am now forced to use that other ESP8266 port from before. This one has the USB to UART converter built in, as well as the 3.3V LDO. After plugging it in, I managed to flash it with the newest release of ESP-Link, using the instructions from the release page. Links to all of the software mentioned in this video are in the description. Now, ESP-Link is a very feature-rich piece of software, and understandably, it needs some configuration. I started out by connecting to the newly created access point with the SSID of ESP something something, then I opened 192.168.4.1 in my browser. After choosing Wi-Fi station from the menu on the left, I changed the Wi-Fi mode from AP to AP plus STA, which meant that besides acting as an access point, the ESP module would also connect to another network and act as a client. I then associated it with my home Wi-Fi. I later changed the Wi-Fi mode to STA only off camera, so that configuration could be done through my local Wi-Fi network only. This is all the configuration needed on the ESP side of things. To test this Wi-Fi to UART bridge, I used SoCat to create a virtual serial port on my system. If you want to know the exact command or how to do this under Microsoft Windows, there's a link in the description. I then opened this newly created serial port using the screen program, and despite furious keyboard mashing, nothing happened. This was to be expected, as nothing is connected to the ESP's TX and RX pins. Instead of searching for something with a serial port, one nifty trick is to just wire TX directly to RX, literally looping the transmission back. You know, as in loopback. Now, typing anything causes the same message to be received. Cool, everything works. Okay, so after testing, all that is left is to wire everything up. I never liked soldering wires to connectors directly, because they like to move, even when using a third hand, or, in my case, something heavy. That being said, I think this one came out alright. I even used some heat shrink. I connected everything according to the front panel silk screen markings, even remembering to cross TX and RX, as one side's receiver should be connected to the other side's transmitter. I plugged in the power and nothing. The unit powers up, there's no doubt about it. You can hear the relays clicking, but nothing lights up. After a quick investigation, it turned out this same UART cable is used to supply 5 volts to the front panel. Nothing I can take care of, and I guess I was kind of lucky, as I had completely forgotten about adding that voltage divider on RX, so had the front panel had 5 volts plugged in, my ESP8266 would be fried. After fixing that and soldering up a Y-splitter wire off camera, I had all I needed to make this thing work. I even attached the module to an unused screw hole using a self-tapper I cannibalized from the main board. You see, everything is connected properly. Right? Right? Son of a... Okay, I fixed it off screen. And after all that, it finally worked. Now, instead of showing you a boring recording of me controlling the wavegen from my PC, let me demonstrate a cool function of my Siglent oscilloscope. If you have a compatible Siglent wave generator, you can create bode plots right on the oscilloscope, which is pretty neat. Obviously, my field tech is not compatible, but someone wrote a Python script which acts as an intermediary between the oscilloscope and the generator, allowing me to use this function with my non-Siglent generator. And well, here it is. The bode plot of an RC filter, done in a very hacky way. Tune in next week for a comparison of two very nice but budget-friendly oscilloscopes. My Siglent SDS1104XE and my friend's Rigol DS1054Z. And now I leave you with the footage of me ferociously trying to insert USB plugs.